Hi, it's Dave. Welcome. Today, I'm joined by James Douma, a machine learning specialist and also a Tesla investor. We've been doing these talks over the past few years on Tesla's AI endeavors, especially Tesla's full self-driving program. And in this video, I want to highlight and really focus in on Tesla's latest version 12 of FSD, or full self-driving, that Elon Musk previewed recently. So I want to welcome James back on the show. How are you doing?
Great. It's great to see you again after all this time.
Yeah, it is. So we're doing this interview in person. I love in-person interviews. It's like so much more information, or just back and forth. We're in Ontario, California, and Southern California. So yeah, it's good to be in person again too, I think. First, I want to talk about FSD 12, Tesla's latest beta version, and then talk about perhaps if this changes the trajectory of where we might expect Tesla's FSD to be at in a couple of years. And then maybe end with some kind of bigger picture, what's going on with AI in the bigger picture. How does Tesla's efforts fit in? So yeah, let's dive in. I guess first question is version V12. So when Elon Musk previewed this on Twitter, what was kind of your first reaction? Was it like moderate, or was it super excited, or was it just...
It's really exciting. Mm-hmm. It's a significant deviation from how I was expecting the program to evolve over the next year or two. I mean, we fall into these traps where you see things sort of proceeding in a certain way, and you kind of expect that to continue. And this, pulling the last bits of code out, and no small amount of code. They talked about 300,000 lines of C. Like pulling that out, replacing it with a neural network. I mean, it's a really significant step forward, kind of functionally, in terms of like what you can do with the system and how you train the system. But it's also a point I was, they were always going to get here. Like it was always going to be end to end at some point. It just is. But there are parts of the process that are easier and parts that are harder. And there are parts that you have to build first before you build other parts and that kind of stuff. So, it was always going to be, I mean, the first people to succeed at this were going to be people who started building modules, put the modules together, and then gradually sort of converted more and more of the modules over to code. Essentially, what Karpathy was talking about in his Software 2.0 idea. Mm-hmm. And that's what we've seen them doing. And on the trajectory that they were on, I mean, we saw them do all the perception and get that in a neural network and have all the planning, pretty much all the planning in code and whatnot, and then gradually adding neural networks to enhance these later functions, planning and later control. And I was really surprised to find that, in one sort of step, because I was expecting this to take another year or two or something like that. But like in one step, it was just like they were able to like take all the remaining heuristic code and drop in a neural network trained in a particular fashion. And because that's the last, that was the last non-neural network block that was significant in the control path, now you can do end-to-end, because once it's a neural network from the input to the output, you can back propagate, you can train through the whole thing as a single unit. So that, like, it has a lot of really interesting possibilities for the future. And they wouldn't have made this change if it wasn't a significant improvement, because it would have been safer to keep doing the other thing. So we know, we heard from some of these book excerpts right now a little bit about the timeline. It wasn't that long ago that you can bet that they were looking at various approaches to doing end-to-end, like throughout this program. Mm-hmm. Because once you can get it working, it simplifies a bunch of things. It's a big lever on a lot of different kinds of making, a lot of different ways of making the program move forward faster. And so, just like a lot of other entities that have looked at end-to-end or whatnot, you have to get a certain amount of traction on the problem before it starts to be practical to try doing that. Mm-hmm. And, so about a year ago, it seems like they had a new approach for dropping in, the last block. and they took a look at it and they thought it was promising, and then they did a significant amount of work on it. It sounds like they worked on it for about 4 months, including a significant amount of data development and testing and that kind of stuff. And at the end of 4 months, they were getting good enough results. And that was like last April, that they felt like that, well, at least, the anecdote is that Elon decided to like shift the resources and focus on that as a primary path.
Okay, so let's dive into this a bit more. So for those who maybe are new to FSD, so the three kind of components typically is the perception, is basically figuring out what's around you visually, identifying objects, also what Tesla called vector space or occupancy networks. And then the second part was a planning. How do you navigate kind of those routes? Like how do you pick the best and safest route? And the third part is controlling the vehicle, right? Going forward or turning or braking, etc. And so initially, a couple of years ago, Tesla was really focused on the perception problem and really changing all the heuristics over to an AI, a neural net model. And can you kind of explain for those who are kind of new to this whole FSD process, like what was the big focus previously, let's say up until maybe second half of last year, in terms of just the perception part? Like what did they need to do to really nail perception and really understand their environment, accurately enough where they could move on to the second part of more planning?
Yeah, you probably can't reduce it to a single thing. Like a lot of these kinds of engineering problems, there are lots of little details that you have to get right. I mean, at the top level, you can describe perception as well. You have a neural network, and I want to be able to put pictures in it. And then I want what comes out of the neural network to be a description of the current situation the vehicle is in. Mm-hmm. So that has to be an accurate description of the environment and also predictions about like what is happening. So what is happening is not just, where is a pedestrian, but what is the pedestrian likely to do over the next few seconds? Because those are things. So all of the inputs you need to make a plan about how you're going to achieve your objective. So for a car, the objective is to go a particular place. So perception's job is to provide the planning system with all the information that it needs to come up with, given an objective, what's a good plan to move forward to. And then it hands that to control, and control actually manipulates the vehicle to get that stuff done. So all of these parts can be done with neural networks. Perception has to be done with a neural network. Perception is one aspect of this, especially when cameras are your input, where just like heuristic techniques just don't get any traction at all on this. In fact, it wasn't until neural networks started actually working pretty well that it even became viable to do this. And we've talked in the past about how, 10 years ago, we couldn't build a computer that could tell a dog from a cat. You just couldn't. Like, it was an unsolved problem. And neural networks basically slam dunked that. So extending that gives, provides all of these perception functions. It, where are the signs? Where am I in the environment? Like, what things are related to me? What trajectories is everything? All of this is perception. Okay. So they had to get perception. They started with perception. And because planning is something that you can tackle with heuristics, and control is certainly something you can tackle with heuristics. In the beginning, it was just like, let's get perception working so that perception is giving us the information that a heuristic planner needs to make to make plans that it can give to a heuristic controller and see where that gets us. And they did that. And up through V8 and V9, like that was really the central focus of what was going on.
Mm-hmm. So heuristic, for those, again, new to FSD or to AI, is more rule-based programming. So it's basically defining, all the different trajectories of, I guess, how to make certain conclusions. So neural nets, Tesla really nail or focused on that with perception. And I guess the past few years, we've seen it kind of shift from the single frame to video to more of a 3D kind of occupancy network or vector space interpretation. So Tesla's able to reconstruct from their camera systems, like the entire kind of 3D space almost around the car, also where things are moving in what direction, so they can make accurate predictions. But then the stickler was still planning, because the planning section was still had a lot of heuristics, or mostly heuristics, right, up until year or two ago. And then they started, I think at last AI Day, they really started to show a lot more development with changing over the heuristics of planning over to neural nets. They're showing, different things like the language of lanes and et cetera, to help with planning. But I think what was shocking to me was it kind of signaled at last AI Day that this is going to be a gradual progression over time where neural nets would slowly eat the planning stack. And so I was thinking, okay, after a year, next AI Day, we'll have like 70% of the planning stack or something artificial, neural nets, and then it'll go to 80 or 90 or 95. But what's interesting with the V12 is this big jump. They're like, we're not going to focus on the incremental, switching over from heuristics to neural nets. We've figured out a way to just make the big jump, right? And when I heard that, I'm like, okay, that's good in theory, and but let's see if it really works. Because if they can get it to work, then there's a lot of implications. It means that they figured out a lot of different things to make it work that are very challenging that they were never able to really figure out before that. There's something that happened that allowed them to make that jump where they didn't have to just incrementally, do another 10 or 20% in the planning stack and move up. So, what's your take on that? Like, what do you think Tesla figured out? Or was it just that they had enough of their neural nets developed with perception and some with planning that they had enough where they could just, try an experiment to go end to end and it started to work with enough data? Was it just kind of a natural thing, or was there some type of technique or I don't know, something you think they uncovered?
It's probably a combination of that stuff. So if you have all the other blocks, any one block is easier. Like if you have them in the sense that you're getting good results out of them. Building a perception stack that produced like what they'd called the bag of bits, which is just like all of these zillions of descriptions of all these distinct objects in the environment. Like that, getting to the point where you can do that, you have to solve a lot of problems. And then when they in V11, like one of the things that we heard was that they went from having that bag of bits. It used to be that they had heuristic code. We talked about this in the past, where they'd get the bag of bits, and then they need to make a vector space out of a list of all the objects and stuff. Because the bag of bits itself is just like, it's too big and unwieldy. Like it's literally thousands and thousands of these sort of distinct identifiers. And if a program written by a person running on a small computer in a car has to deal with all that, it's first of all, it's complicated, it's brittle, because it's brittle because it is complicated. You have all these complicated rules interacting, and you get these, weird interactions between them, and then you have to debugging. But it's also very time intensive. Like that can't run on a GPU. It has to run on a CPU. CPUs are relatively slow. They only have so much power in the car. So that was a limiter. So with 11, they moved that over to basically a neural network that would take the bag of bits and make the vector. And so that was a pretty significant step forward. Now, for each bit that you've got solved, the remaining bit, like in a sense, that gets easier to tackle. Well, planning is hard. Planning's not as hard as perception. Planning is hard in kind of a different way. We've been doing planning in AI with heuristic algorithms for decades and decades, and it's a reasonably well understood field. But it's got its limitations. And when you're dealing with a problem that's as complicated as everything that can happen in the real world, even these relatively mature algorithms, they really struggle to get the kind of completeness and accuracy, perfection that we want to have when you've got a safety critical application that you're dealing with. So I think it very much is the case that what they got done with all of the stuff up to the vector space, being able to get that into a neural network and get it working well enough that V11 is possible. V11 is quite good. V11 is a remarkably good, piece of work, especially considering they still have 300,000 lines of code in this planner, right? Like it's hard to get 300,000 lines of complicated code to work in the kind of flawless way that you want it to in a complicated domain. So that enabled the possibility that you had now reduced the remaining part of the problem small enough down to just 300,000 lines of code, down to just taking the vector space and making a plan that you can hand to the controller, that now it becomes viable. So the more you do, the more potential there is for one step to take you the rest of the way. Now, that doesn't mean it's guaranteed to happen. It just becomes more likely. And so I imagine all along this process, there were people trying to see if they could do it in one step. And I think Tesla themselves, as of last AI Day, they weren't expecting this.
Yeah.
I mean, the timeline that we heard was that sometime around December last year was when they had somebody on the team had something that looked like it had the potential to close the gap and let them do the rest of it. Yeah. And even then they didn't know. I mean, you never really know until you get there, because it's a really complicated problem. And this the problem of driving cars is it's continued to surprise us. Everybody's been wrong. Everybody who was on the it's going to happen side has been optimistic. They've the technology has failed to meet their timeline expectations. Yeah. Because we keep discovering that the problem is harder than we thought it was, but we are closing the gap. I mean, you can see that the number of interventions comes down and down and down. The number of, if you've been using the technology for a while, it's clearly growing by leaps and bounds. But when do we get that last little bit? Yeah. So being able to put a planner in there that you were pretty confident could close that gap entirely, because you don't want to switch approaches to something that isn't going to get you there. Right, you're only going to switch approaches to something that you're pretty confident is going to get you there. And one of the reasons I'm very enthused by seeing this step is because it's Tesla must be feeling like they now have all the pieces necessary to put that last block in place, and now be able to train the thing as a single unit. Like, once you've got that last piece of neural network in the middle of it, now the whole system is a neural network, and you start being able to refine and improve the system, not just through training, but through some kind of incremental architectural changes, so that you're within reach of the goal. And now it's just a matter of further refinement. It's really exciting that up until now, they have been betting on a sequence of, we'll call them mini innovative breakthroughs. They've needed the engineers to go back and look at it. Like, every time they plateaued, they got to a local maximum. They needed somebody to go in and find a clever way to break that and to get out of it, because it hasn't been sufficient to just put. I mean, turning the crank on Karpathy's data engine, it gets you a lot, but they would occasionally bump into places where it wasn't good enough and you needed something else, and a human had to get in there and start fooling around with things, had to change the way that stuff was being done in order to continue making rapid forward progress. And so my sense is that with this completion, they've entered a new domain of where there's a whole new set of tools that they didn't have before that they can bring to bear on this problem. And I do expect it to accelerate progress.
I mean, my kind of first impression was I was really, really impressed by V12.
It was really good. It was much better than I thought it was.
Yeah, because I would expect an early version to be fairly, really buggy on lots of different things, but for only one intervention to happen, I'm like, wow, they figured out end-to-end in a way that's this reliable at this early junction. And considering, just theoretically, considering how much more potential there is if you move past heuristics into kind of purely neural nets, it seems like this is kind of the defining moment for FSD in a way, this V12 jump, meaning everything before V12 was kind of almost, one by one building these different subnets or neural nets to do different things and to make it just functional, decently work. But there's still these it still had its issues, its rough edges, and it still wasn't good enough for prime time, especially in, mass rollout. And it seems like V12 with the end-to-end approach, with relying on neural nets completely, that this is a new era, a new stage, a new period of FSD. And if they've already gotten it this good, it just seems like extremely optimistic where it could be in a year or two. I mean, what are your thoughts on that?
No, it's really promising. I agree. If I had guessed, what the level of performance they'd be able to get after a few months of making this big a change. It would not have been that. And what I take from that is that the approach that they're using for both, the way they decided to do planning and drop it in there, and the deciding to mimic humans, right? Because there are other ways you could have done planning. You didn't have to mimic humans. I mean, a lot of people have done that. If you can get it to work, it's great. There are a lot of things that we really understand about it. But there are other possibilities. I'm sure that they looked at other possibilities, but they have an approach that seems to be working really well. Like I would guess that, most practitioners in the field would look at that and would be surprised at that amount of progress in this relatively short period. Now, when I say that amount of progress, we're extrapolating a lot from a single demo, right? We saw the car driving for 40 minutes or something like that with some stuff. And, if you've driven FSD a lot, you can get a lot out of that video. Like you see all of these little differences that speak volumes because we've watched it evolve over the last few years. And there are some very persistent issues that it had that it didn't seem to be making, rapid progress on, which almost seemed to be solved in one fell swoop. Like the smoothness issue, that's something non-technical users really hate that. It's really not confidence inspiring to see the vehicle doing stuff where you think it's confused, that make you think it's confused, that it's about to do something unexpected, right? If it behaves like an uncertain human driver, as opposed to an uncertain machine, like that's a much more confidence inspiring thing. You kind of know what the boundaries of what it can do, and also just having the ride be smoother, and having the body language of the car, the way it moves through traffic, mimic human drivers better. That's going to make other drivers more comfortable. It's going to integrate with traffic a lot. There's a lot of benefits to this, and it seems to have suddenly picked up a lot of abilities, a lot of important features that they just hadn't been getting as good a traction as we would have liked on. Like you could have asked, is it ever not going to be jerky? Right? Because we've seen it get better and better and better, but it seemed like that Zeno's paradox thing, you're almost like you're never going to get there. It's just going to incrementally get better. And 12 seems like it just took that off the table.
Exactly. Yeah, it seems like before version 12 or before, this year, the idea was, could Tesla reach FSD Robotaxi with, depending on some level of heuristics, in the code. Obviously, vast majority AI or neural nets, but with this, and then there's always this question mark of like how long that would take, because progress for a lot of people isn't like, it's debatable like how much progress is being made and how many more edge cases need to be solved before we can reach Robotaxi. But I think this shift and this almost sudden shift to end and kind of disposing or pushing aside the heuristic, the rule-based stuff, it kind of, I don't know, I think it opens up, it uncaps the potential, meaning, or it releases what's possible for AI driving, meaning before there was always some level of heuristics kind of safeguarding it or bounding it, and the neural nets had to kind of work with the heuristics and the code, the rule-based code in the system. And there was always this kind of a hybrid system that wasn't per se reaching its potential in a way. But it seems like just looking at it just theoretically, the end-to-end approach finally is the thing that will, make it a pure AI kind of play where you have data, the training will be adding compute and data and pushing that through, and just kind of the law of scaling too. It seems like before with heuristics, you had to kind of, there was an additional kind of human element into all this. But now you've kind of removed that. Now you could just double down and go crazy on compute and data and training. And it seems like you would see like a really big improvement rapidly. I mean, what's your kind of take on that?
Yeah, it has a lot of implications, this change. I mean, we don't know if, there's another hurdle farther. In fact, Getting better than human, yeah. So they get hit, they get there with 12, maybe. I mean, in many respects, 11 is already much better than a human being because humans have so many sort of really glaring weaknesses, distractibility, being a major component of that. There are all kinds of problems machines just don't have, and so they get a big advantage there, right? There are these where humans shine is when you get these really complicated situations, right? You come to an intersection and there's construction going on. You're in the middle of a rainstorm and a tree is down, right? And you have to make a decision about, like, do I even try to continue on this route? Do I go through the parking lot of this Ralph's instead of trying to traverse the intersection? I mean, there's this large space of possibilities that a human can bring to bear when you're reasoning that are very hard for a programmer to anticipate ahead of time. So do we get there just by training on, good human driver examples? Maybe we might. Like, it's certainly got the potential to get there. But a lot of, AI practitioners believe that you need to also add reasoning, that reasoning is somehow separate from these other things and that in the long run, that's going to be necessary. Well, they're not trying to do reasoning right now. They're still, V12, everything it's doing is still in the realm of reflexive driving. And that's almost everything humans do. Like, virtually all the driving you do is reflexive. It is really rare for a person to encounter a problem when they're driving a car where they have to stop the car and think hard about what they're going to do before they proceed. It does happen, but that's uncommon. So you probably don't need that for robotaxis. I'd say it's quite unlikely that you will not be able to make a useful, commercially viable robotaxi without reason. That said, if you have reason, it's better. You get maybe you go from 5 times safer than human to 25 times safer than human. There's going to be value in there, and it's going to get added at some point. And so there are things that V12 probably doesn't give us in principle, right? It does give us a whole lot that we haven't had up to now, like this particular approach. And I think there's a very good possibility that it is going to resolve the remaining obstacles to being able to roll out a robotaxi fleet, even if that fleet isn't perfect. Even if there are still situations that it can't deal with. If you can do, what 99.9% of Lyft rides does, that's good enough. That'll solve a lot of problems for a lot of people, and it'll be really valuable, and it'll get a lot of internal combustion vehicle miles off the road, right? Because it'll, it's the start of the phase transition to being able to have self-driving vehicles start taking really large fractions of the burden of driving off of people.
Yeah, I think it reminds me with ChatGPT. I think the thing that kind of shocked the world with ChatGPT wasn't its regurgitation of what it's been trained on, but its ability to apply human-like, it feels like, reasoning or thought analysis into new topics or things that really shocked people of its ability. Same thing with GPT-4. And obviously there's a debate of can, GPT-4 reason like a human? Most people will say maybe not. But there's another angle where it's, well, GPT-4 seems to have a level of understanding of what you're asking and the situation that is kind of shows a different type of reasoning, perhaps, where in order to understand the complex whatever prompt or situation that you're giving it, and to answer that, there's just to have that level of understanding, it implies a type of reasoning, that it has to have in a sense. But applying that to FSD, like early stages of version 12, I could understand. It's just what you're calling reflexive driving. It's not per se understanding or reasoning to a level where it's like it can necessarily cross-apply all of its understanding to different situations. But would you say at a certain level that its understanding over time, let's say in a year or two, it actually starts to understand why it's doing what it's doing? Like, different situations, different intersections, like it understands why this is a safer route, and as it grows in understanding, then it can apply that type of reasoning to extremely difficult situations that it seems like, whoa, this AI is reasoning, because it just seems like it's not something that could just be reflexive. Do you see that kind of coming anytime soon?
understanding is a word that we use in a lot of different ways, right? Because human understanding isn't just, making decisions via logical rules. It also includes a ton of intuition, like all of the stuff that we do from a practical standpoint in the world. It's a combination of these two things. And it can be really hard to say where the line between those two things is. I like this metaphor of like learning to play tennis, where like in the beginning, you're so aware of all of these trivial little things, like exactly how you hold the racket or where your feet are on the line and whatnot. The more you play, the fewer things you're aware of in that sense, and the more your awareness, your conscious sort of sense of presence of the game shifts to these more and more abstracted things. And it does that as your kind of reflexive understanding can take over more and more of the burden. It frees you up to do stuff. Good tennis players, like if you've really played for a long time, you don't think about the ball or the racket or whatnot. Your mind is occupied with the strategy. Is my opponent wearing down? Where are his weaknesses? Like, do I want to make him try to go out of bounds? Is he bad going back? And then, you sort of sort of intuitively understanding the flow of the game and directing the flow of the game to take advantage of what you see as the vulnerabilities of the other side. So that's on a completely different level than how do I hold the racket and do I want to use topspin right now? Like all of that stuff completely goes away as you learn more. Driving is a similar thing. There's, in the beginning, you're super aware of really small details. The better you get at it, the more and more of the problem descends into this sort of reflexive driving. So where is the boundary? The car's more impressive the less good you are at driving, the better you are. Like if you're Mario Andretti, then even really complicated things probably don't impress you. Like there isn't really this clean line that we can draw where we can say on this side is understanding, on the other side isn't. If the stuff that they're doing, like, as it continues to get better, it's going to display more and more of what we see as understanding. This is the same problem, the question of whether ChatGPT or GPT, whether it understands, whether it has reasoning, that's an open question. Like experts, people who study this, who their life work is, they do not agree on whether it's understanding or whether it has the potential to do the same kinds of reasoning that human beings do if we just use it the right way. And that's part and parcel of this whole era that we're in right now. We're using this new super powerful technology that we don't really understand the implications of any of the stuff that we do. We don't have theories that tell us really fundamentally what it's capable of. We use it, we learn things, and we're constantly being surprised by it. And the more we're surprised by it, the less we believe we really understand what the limitations are. And the ChatGPT moment for language models, it did that to all of us, right? ChatGPT is not better than the GPT-3 that came before it. Like not in terms like all of the stuff that you can do in terms of measuring benchmarks, reasoning, all of these simple reductive cognitive tasks that we like to use as benchmarks. It's not better than GPT-3. So why does it seem so amazing to us? Like why is
GPT 3.5 though? Right?
Yeah, it's GPT 3.5.
Okay. Yeah,
but the thing is. The difference between ChatGPT and the foundational GPT-3 before it was taught to interact in a human manner with people. And that made us as humans, because that's our natural way of interacting, so much more aware of what the potential was that was inside this thing. It didn't create a capability so much as it revealed one, and suddenly we realized it was there. We will see similar things with FSD type technologies or other neural network technologies, right? When they're doing human comparable activities, things that we can look at and relate to and understand, once they start doing it in a human fashion, all of a sudden it seems like it's had this great leap forward. And I think one of the reasons V12 is as surprising as it is because it's kind of doing the ChatGPT thing. Like it's much more speaking the human language of driving and maneuvering in a car than the kind of mechanical robotic thing, which might have been functionally equivalent in terms of, say, interventions or accident probabilities, right? But to humans, it wasn't relatable. And V12 will be, and we'll get that. But like more importantly, now that loop has been closed, and because this was a thing that happened with language models too, and NLP, natural language processing. For a long time, up until GPTs started really gaining traction around GPT-2 or whatnot, what the field thought natural language processing was going to be is that we were going to have this language model. That's why these things are called language models. It was just going to do the language part of the thing. But to do real work with it, you were going to have this big heuristic thing that sat on the back end and had it had databases, and it had these rules that were written by humans. And it turned out that the language model, that was sufficient to actually do all of this other crazy stuff. Google did this amazing thing with Palm, which it's an experiment in the robotic space that I think doesn't get enough attention. They took Palm, which is a big language model, like 600 billion parameters or something like that, and then they took this image model and they bolted the two together, and then they took like this robot proprioception model and they plugged that puppy into it. And the idea of the experiment was, there's an awful lot of common sense, what we think of as common sense, that language models just get because they read all this text. Like they learn all this stuff about the world, right? Can a robot make use of that? And it turns out it can. It was a very straightforward process to basically get a robot to use the reductive capabilities that the language model had learned to make decisions about, like, well, how do I go in the other room and grab a bag of, how do I get a beer out of the fridge? Or, you've got to break that down into all this stuff and then turn it into, rules, individual movements for all the motors in the robot. And they could do that. So that basically shows that once you've got neural networks from one end to the other, there are these synergies that start to pop out and these new capabilities that start to emerge. And I'd be shocked if we didn't see that kind of thing with self-driving. Because one of the I think really beautiful possibilities now that they've kind of gone end to end. Once you've gone end to end, you have this sort of these models, they have a thing inside them we call a latent space. Typically, you take your inputs and you convert them into this kind of conceptual space, and then you have another neural network that takes that conceptual space and turns it into the actions that you want. But it's in that conceptual space, that latent space, that like the neural network is manipulating the ideas. That you want to get the shape, get it right. You want to get your input so that you're creating the right latent space that can easily be converted into the decisions that you need for the output for the problem that you have. So one of the things that Google showed with this Palm demo is that if you've got a latent space for language, and you've got a latent space for images, and you've got a latent space for the robot things, you can glom all these things together, and they can all talk to the same latent space. So you can have language go in and robot actions come out. Hey, go get me a beer, and it does the plan, and it does that. That's what these text-to-image models are basically doing the same thing. You train a text model, it has a latent space. You train an image model just on images, it has a latent space. You show it a little bit of how the crossover works between the two, and you can merge those two latent spaces. So one of the really wonderful possibilities that comes up is, because language models are already showing us, they're giving us this ability to build a latent space that has all of the common sense and human interactivity and whatnot that we're now seeing with GPT-4. Why can't you use that? You can totally use that with a self-driving car model, so that you can be sitting in the car and you can say, could you slow down? Could you pull over here? Would you, hey, I'm in a hurry, I need to get to the airport. And you will literally be able to talk to the thing. And the language model takes that and it puts it into the latent space of, like, what does that mean to the driving model? If the driving model and the language model are in the same space, all of a sudden now, and that's a thing that you really can't get to easily with heuristics. Yeah. Right. So that's just one example of a lot of possibilities. Or this other thing that Ashok suggested, where, have the car come to me. I want it to know what my face looks like. And I'm going to walk, I don't know where I'm going to be on the corner. I want the car to come and get my photo. Well, all of a sudden I can take an image, the latent space from, an imaging system, and add that to what the car has. And all of a sudden the car now has this extra, like, the cars haven't been trained to distinguish between individual people. That's not part of V12 training, right? Yeah. But I can have a separate model that has a latent space for that, put those two together, and they can interact.
Yeah. Yeah. I mean, it's interesting because, a lot of these neural nets are becoming more multimodal over time. Like, pretty soon we'll see GPT-4 released with its more or image generation, image input, even Midjourney. They're like, you think that they're focused just on video or images, but they're actually doing a lot more incorporating language and understanding language to help generate better images. So it's like whatever you could do to add kind of this capability of greater kind of understanding, it helps, the final output. I think it's interesting with FSD is because if Tesla can get this good already with kind of video, who knows, maybe a video is good enough, maybe just seeing more and more situations, it gains more understanding, it adds kind of that across different scenarios. But there's also this possibility you add, as you're saying, other neural nets that can, in that latent space, that can add better reasoning. It does kind of another jump or more jumps. And with more compute, you can add more parameters, have bigger neural nets, more neural nets, add capacity. I'm not seeing like with more compute, there's a downside right now, So it just seems like it's opening up a lot of options for FSD right now with going, all neural nets. I mean, what's your take?
Yeah, it's the possibility space is really opening. It's hard to think of things that aren't possible, like the mind. When it occurred to me that you could take that latent language, space and glom it onto the car, and like I couldn't think of any reason. Like, we talk about speech being a modality for these models. Text is a modality. Almost all the big language models are just trained on text right now. When you add speech to it, they get better. Like, because they know what language sounds like, and language for human beings is fundamentally it's an acoustic. The phonetics of language really matter, and the phonetics aren't really captured in text, certainly not in languages like English, which are not phonetically written. You add images as another modality. Driving's a modality, right? Yeah. To a human being, like the degrees of movement and the space that you're in, those are also the modality of like being in a physical, humanoid body in a space, and that's something that will apply to robots. It's another latent space, another modality that can be combined. Any of these things, potentially, you put them together, and all of a sudden there's all of this cross-pollination between these two capabilities that you get. And so, language and driving, like that's an obvious huge win for a robotaxi. Yeah. So a customer can get in and say, don't take the freeway. I hate the freeway. Yeah. And the car will know what that means and be able to respond to it in the way that the passenger expects.
Yeah. What's your take on Elon's quote saying that if you put Tesla and OpenAI head to head, meaning if Tesla was put in charge of trying to develop an LLM, large language model, like GPT-4 or whatever, and you put AI or OpenAI in charge of FSD, Elon saying Tesla can knock out, the LLM quite easily.
It wouldn't even be a contest.
But his conclusion is kind of saying that Tesla's AI chops are, in a way, almost he's saying it's kind of stronger, or Tesla's doing a much more difficult, in his opinion, kind of AI task. What's your take on that? I mean, it seems like it's hard to compare these two because they're just, right now at least, very, very different. And OpenAI just has such a large lead on the LLM side, is that I don't know if you could just simply say that, full self-driving is harder per se, because it's also at what level they're trying to pursue the capabilities of LLM too. So, can you even compare, what Tesla's doing to OpenAI?
I think that sort of hypothetical of, if you took OpenAI today, just with their resources, and they had to do FSD, like how long would that take? And if you took Tesla today, just with their resources, how long would it take them to do LLMs? It wouldn't be a contest. There's so much infrastructure that Tesla has had to build. Like physical infrastructure, as well as all of this expertise and all of these sort of niche elements of the problem. They each just take time. You have to work through them. You have to try stuff. As I mentioned before, it's empirical. Like a lot of the exploration in the space right now is you try stuff and it doesn't work. but it gives you an idea, and then you try that, and that doesn't work, and you get 3 more ideas, and you try those, and gradually stuff gets better. There's this it can be super labor intensive, like turning the crank. And I think both OpenAI and Tesla have this reputation for really smart people work really, really hard. OpenAI is working on a narrower problem, and their OpenAI is working on a problem where there's an enormous amount of public knowledge about how to go about doing this stuff. I mean, the basic formula for these language models is known. There's a lot of details of how you train them, how you curate the data set, what's the right loss function. There are all of these technical details that involved with actually getting the thing to work really well. But that said, there are lots of people outside of OpenAI who make really compelling models, and they haven't been doing it for 20 years. A lot of these, external organizations just, 2 years ago, 3 years ago, they managed to get up the curve. Did they catch up? OpenAI's got a head start. They're moving really fast. Maybe nobody ever catches up, but can other people make useful, large language models? Well, absolutely. I mean, we've seen many of them already. So could Tesla do that? Yeah, it wouldn't be super hard. You could take public formulas and public databases and basically replicate that kind of stuff. If somebody else wanted to do what Tesla is doing, okay, first build a factory, make 1 million cars. Get a bunch of guys in a room. Spend a lot of time interacting with a population of real users in the real world using this, because a lot of what the AP team has learned from using FSD is interacting with the user base, learning from how they use the product. That just takes time. You got a lot of drivers on the road in a lot of situations over time, and you learn and you refine stuff. So there's a time component that it's integral to a lot of the stuff that Tesla's done, and very little of what they've done is public knowledge. I mean, the code hasn't been published. There aren't a lot of people who've left the FSD effort who are writing books about how to make an FSD car, which is totally different than a language model space. So in a sense, it's kind of unfair, that what OpenAI is doing is in many ways, the underlying tech is a lot more public. But I would totally agree with that assertion. I don't think OpenAI could catch Tesla I don't think OpenAI could make an FSD that's as good as FSD 11 in the amount of time that it would take Tesla to make a GPT that was as good as GPT-4.
Yeah. I mean, a lot of I think the angle also is Tesla has a lot more complicated moving parts with, for example, you need an inference computer in the car that takes low energy consumption and is extremely quick. You have to there's things that it's not purely just, a server and people. It's a much more complicated ecosystem of different things that need to work all together. So it's harder to copy in a sense. You could whip up an LLM startup in a year or two with the right funding, come up with something interesting. But yeah, with FSD, you need the cars, you need the data, you need the video, you need the hardware on the computer, you need and the safety, and also these safety critical applications, they're extremely difficult to roll out.
There are aspects of that problem that you just have to approach a different way when it's safety critical.
Yeah.
I think OpenAI thinks a lot of what they're doing is safety critical. Maybe not today, maybe not right now, but that there are safety critical implications. And that's something that Tesla doesn't really. I mean, FSD is, it's pretty advanced, but nobody thinks it's going to wake up, right? It's not going to be used to make really important decisions in the real world that could affect millions of people. It's just driving cars at the end of the day. That's fundamentally what it does. And of course, the potential for what GPT could be used for, what somebody could decide to do with it, that has implications that the more, in a sense, the domain for FSD is constrained. It's a really complicated domain, and for OpenAI, it's different. So I guess in some sense, your statement that they're hard to compare is true.
Yeah.
But the simple hypothetical that Elon posed is probably true, and it shows Tesla's efforts in a good light.
Yeah. So in the Isaacson book, the excerpt about FSD, it talks about an engineer who in December had this kind of thing of trying to do an end-to-end approach. And in the book, it mentioned that the engineer talked about ChatGPT. It would be like ChatGPT, end-to-end type of approach. Do you think the ChatGPT kind of wake-up moment in December of last year had a part to play in terms of like motivating or inspiring or seeing the potential of what, let's say, an end-to-end model could do if it was applied to FSD? Like, do you think it somehow was a trigger or something, or it helped the process at all?
There probably aren't very many people in the field who aren't inspired by what happened. So yeah, I'm sure that it prompts a lot of stuff. So there's a distinction. GPTs, they're self-supervised. They basically just predict what the next token is. It's described derisively in those terms, but the implications are profound for being able to do that. Yeah. I mean, write me a book, predict the next token. The first word is really hard, right? Because the space of books is really large, and you've got to be coherent from that. So, it's more complicated than it sounds. But that one of the advantages it has is the training methodology is it's pretty homogeneous and pretty straightforward. Build a big transformer, get a lot of text, have it predict the next token. And if you have a big enough data set, enough quality, big enough transformer, amazing things come out of it. Like that's not, a super complicated recipe. Once upon a time, a few years ago, I had been thinking, and other people had been thinking, man, it would be great to do that with vision. You have a camera, and it just looks at stuff, and you train this autoregressive transformer to just predict what happens next. Like if it's watching TV or watching YouTube videos, in order to predict what comes next, much like the autoregressive transformer that is a GPT predicting text, it has to learn all kinds of things about the world in order to predict the next token when you're reading a novel or something like that. A camera looking at a scene, it similarly has to learn about physics, it has to learn about the 3D nature of reality, it might have to learn about human cultural conventions, like will these two people hug, will they fight, like what is their body language saying? It's got to learn all kinds of amazing stuff just from having a camera and trying to predict the next thing. The thing is, doing that trick with cameras is radically harder than doing that trick with text is. I mean, we thought text was going to be hard, and text did turn out to be pretty hard. But we got there a lot sooner than people thought. Once upon a time, it seemed like you might be able to do that. That is not what FSD is doing, right? FSD, the vision system was trained explicitly on a lot of human-labeled stuff initially, right? And so they got a head start on understanding the structure that they needed to effectively create a representation that a machine could use to drive in the world, like that the perception part of the problem. The planning, part of the problem, it has other constraints. Control has other constraints. This final step that they're doing right now, this quote-unquote final step, they're training it to mimic human beings. Now, that's kind of parallel to GPT. Like all books are written by human beings. A human wrote this. Maybe when you're predicting a token, what you're predicting is what is the next token the writer's going to write. You could think of them as parallel that way, right? But there isn't like this vast database of like video and what did the human do with the controls in a car out in the real world. Like they've got to build and curate that database. And in a lot of ways, this is supervised training. It's not. You can think of it in certain ways as self-supervised training, but it's not really the completely generic, we're just going to use cameras and the car's going to learn everything about the world. In order to make it tractable today, Tesla's really narrowed it down to, here's a scene from a certain set of cameras in a car, just tell me what the driver's going to do with the controls next, right? And you collect a big database of what the driver did with the controls and you create that and whatnot. In a lot of ways, that is much closer to supervised training than this wide open thing, and that has implications for the constraints. In order to get it to train quickly, you're narrowing down the scope of the task. The more you narrow the scope of the task, the less the system needs to learn about the world. So the less general of the system that you end up getting at the end of the day, right? It doesn't have to learn as many things about the world.
Okay, so in terms of how they're training this, so you're saying that you don't think they're doing kind of, you're saying they're narrowing it down on what the driver is doing.
It's not basically really doing what GPT does.
Yeah. So rather than like predicting the next frame or next second of perception or planning or control, it's more focused on what is the human doing. Do you think they're doing some type of self-supervised thing where you feed it these videos and it tries to predict what the human will do, and then if it's incorrect, then it kind of like, goes into the training. It kind of corrects it, or it's added, like kind of like, for example, with transformers, GPT will take a sentence or word, predict the next token, next letter, etc., and then kind of it predicts the next letter, and then it's shown the next letter. I guess, in a sense, and then it adjusts its weight.
The input and the output, autoaggressive things, the input and the output is the same, right? And so what happens is you have a big database, and you just remove some of it, and you give it to the model, and it has to predict the missing pieces.
Exactly,
okay.
Yeah.
So GPT does that in the sense that, you give it some text, and the thing you're hiding is the next word, and it has to predict that. And then you give it that word, and then it has to predict the next one. You just have this big body of text, and it's just learning the patterns in it. That's not, if what V12 is it's cameras. It's not cameras in, cameras out. It's not pictures in, pictures out. That would be autoaggressive. And then you just, when you train something like that, you just get, lots of pictures. And I think that this is what, that trying to go autoaggressive was something that Tesla was interested in doing, like as recently as last AI Day. When we were talking about, when they were talking about using nerfs, when they were talking about using diffusion models, what were they going to use those for? Well, what they were going to use them for is to take the latent space that the perception system is making, turn it back into pictures. If you can turn it back into a picture, you can close the loop. Those pictures in, pictures out. It's autoregressive. And if you just have lots and lots of video that's relevant to what you want to do, but that's not what they're doing right now. They're doing pictures and controls out. So they have to make a database of pictures to controls by observing what humans do, like that. That you could do it other ways.
I mean, could you do? Because I also remember a show talking heavily about diffusion after AI Day during this like private Q&A session with investors. Like people huddled around him. He was really excited about diffusion. Could it be that that part of the training is using diffusion to kind of pictures in, it's diffused, and you get pictures out, and then it's like control is, I guess, part of that somehow, but it's not just pictures in and control, right?
So if you were doing the autoaggressive vision thing, what you get out of that is you get a world model, kind of like a language model. A language model, it contains everything you need to know to predict language from language. A world model, a vision model, or in this case, it gives you everything you need to predict pictures from pictures. Like here, I'm watching a movie. What's the next frame? Like that would be the equivalent of, here's a text. What's the next word?
Exactly.
When you do that. And, the thing is that technique has been so powerful with text that, of course, anybody's going to think, well, what if I use that in my domain, right? And if you're working in video, if you're working in pictures, you're going to ask the question, can I do pictures to pictures? Because once you do that, the amount of training data that you have just it explodes, right? All of a sudden, you've just got all this stuff that you can do. And the thing is, to predict pictures from pictures, you're forcing the model to really understand a lot about the world. And once you've got that model, it's really powerful. That model at that point has built a latent space, which is just incredibly capable. And you can take that latent space and plug a control layer into it, do a little bit of training. Exactly. Here's the latent space. This is the controls. So you have maybe millions or billions of frames of video that you feed through it to train the model. But then the amount of specific, here's in this is what the human did in this, that's very small. And so the external limitation of like how many car hours you need to have, in order to train the model, that might drop way down. And that's one of the things at the GPT-2 level. One of the things that was sort of being discovered is that GPT models could build latent spaces that were so powerful that with a very small amount of incremental training, you could tailor them to any particular task and they perform really well because the core training of the model was so powerful. It was so inclusive.
Yeah, I mean, that's what I'm talking about. When I hear, for example, V12 is like trained with video in and then controls out, it feels like it's missing, there's perhaps something in between where just doing video in and controls out isn't kind of developing the model maybe enough high fidelity or accuracy. Like if you had pictures in, let's say, and pictures out, and then you took that model, and then, like for example, with GPT 3 or 4, you had transformers do kind of the heavy lifting of the model training, the foundational model training. But then afterwards, you had this human reinforcement learning on top of it to develop the chat interface and to figure out how people interact and what they like in terms of like style and length and all this other stuff. Could it be that Tesla is doing more of a foundational model training that is not pictures in, control out, but it is like pictures in, picture out or something like that? And that on top of that, they're building kind of the chat GPT equivalent of human reinforcement learning with driver data of how people drive. So the control out is another layer on top of that where it gets kind of the model really like accurate to what humans are liking or used to.
Okay, we only know what they talk about. They could be doing all kinds of things that they don't talk about. And we know that they do things that they don't talk about. So I can't rule out any of these possibilities. There is synergy that you get from using different kinds of data, different training modality. In the same way when you build a single neural network and you use, well, like with the Palm, example with the robot, Google didn't need in this particular experiment to train the robot to plan. They got the planning for free because the language model had already learned about planning. And they basically showed you could graft these things together, and the robot control model could take advantage of the planning that the language model had learned from the language model's training. So similarly, if they train the model that has this latent space, which is understanding the world and making plans for driving a car, if you train the more different modes you train it with, the more powerful and flexible it will become. So, if they train it just with the perception mode, which we know that they were doing that because they did that in 11 and 12, and they have all this infrastructure. We know they have that, right? So they might as well use it. In time, it may end up being a really small fraction of what they do with the whole thing. But today, it's probably a relatively not large fraction. So they've added this other, end-to-end thing, pictures in, controls that. That's another way of training the same model. You can do both of them, and it can learn from both of these different approaches. It may be that in the field, you only use one. You just use the controls. But the training that you did, previously with the other modes, that still contributes to it. Could they have a pictures in, pictures out kind of training, and would that be useful to the module? Yeah, absolutely, it would. It's entirely possible that they have it. It's possible that Ashok was successful in whether he was using diffusion or NERFs or whatnot, in getting pictures in, pictures out, and that they're in part training the model on that. It would definitely be useful. The reason that I think my best guess of what they're doing is that they had perception and they dropped in a planning module, and they discovered that they could get a very effective planning module by doing, pictures in to control out, is because at my understanding of the space is that's a much lower hurdle, and it's much more likely to spontaneously happen. A lot of people have worked on the pictures in, pictures out regressive, autoregressive type of thing. And it turns out it's really computationally intensive, and it's turned out to be a really complicated problem. So if Tesla can figure out how to solve the problem they're trying to solve without needing to do that, that saves them a lot of effort, right? And you could easily be in a space where you get a significant amount of value from that, but you're not getting enough value to be able to get the whole way to the finish line with the product. So you use it synergistically with other things that you're doing. So in that sense, I could imagine that they might be doing a certain amount of pictures in, pictures out, because there could be gaps in the world knowledge that the model develops that aren't well filled in by these other modalities that would be well filled in by that, right? Yeah. It's a really powerful modality if you get that going. It's just really hard to do, and really nobody has succeeded at it. And a lot of entities outside of Tesla have worked on that problem.
Yeah, I mean, also not just pictures, but it would be also the inertial measurement units, right? The how fast the car is going, the speed, the trajectory, all that stuff together with the pictures, and get the picture out.
Yeah, I mean, ideally, you bring all of the sensors for the vehicle in, and you predict all of the sensors out. Like in certain respects, the IMU is easier to predict, and in certain respects, it might be really hard to predict. So you might get a lot of value out of it.
It reminds me a little bit about Midjourney's approach right now to video. So people are all excited about images moving to video. And what Midjourney is trying to do, generally speaking, is they're trying to solve actually 3D space first before they transition to video. I mean, they're trying to stuff with video as well, but their kind of theory is if they could solve 3D generation first, then video is kind of movement within that 3D space. Therefore, they're going to be able to solve video. And so when I think about that approach applied to FSD, it's like if for example, it seems like on first glance, it would seem like, oh, V12 is a departure. But in some ways, if you look at it as just the next step, where let's say Tesla is just hypothetically training a more comprehensive, let's say 3D vector space model that's able to, not just predict or see 3D vector space, but do it on a much more accurate level through, let's say, whether it's diffusion or NeRFs or whatever. And one of the results of that is they get a better kind of more confidence with the 3D space, which allows for the control training to be more easily done. So they could, model off of people.
Kind of a different way. So the task of driving a car is much more fundamentally dependent on understanding the world as a 3D space than doing video is. Certainly, if you're doing video and it's video scenery of, people in space, objects in space, scenes of the real world or scenes of cartoons that are mimicking the real world or whatever it is. Okay, well, there's an underlying three-dimensional constraint on what can happen, and understanding that constraint makes the model a lot more powerful. It's much more fundamental to cars. In fact, so, Tesla started out trying to do single frames, and then later they moved on to video. But they really started to get much better when they started doing bird's eye view. Bird's eye view forces the network to understand the world as a 3D model, right? And I would argue that when they went to bird's eye view and when they went to bird's eye view, that was Tesla's, development team basically saying, we got to nail the 3D thing. Bird's eye view requires the model to understand the 3D nature of the world, because you're asking the model, show me what this looks like from a different angle than any of my cameras can see. It has to figure out that the world is 3D or it just can't do that. And so when you challenge it to do that kind of stuff, you force it to realize that the world is 3D. And once it realizes that, all of these other functions of the network can build on that. A lot of training these models, like developing capabilities in the models, is how do I guide the model through its training and its architecture to realize something, to understand something that we humans know to be true? Because you can't just tell it that something is true. Like, it has to figure it out on its own, and you have to figure out what's the curriculum that I give it to get to that. Okay, self-driving cars, they got to get to 3D really early, and they have to have it. It's super fundamental to what they do. So what Midjourney is doing today, because it's less important, is probably something that Tesla was having to nail back when they were doing birds. So I would sort of, it's a useful metaphor, but it's a little bit backwards.
I would definitely agree. But I guess the point, the idea being is that with Tesla's V12, there could be different dynamics going on where it could be their 3D, let's say, modeling of the world has improved through some different techniques. And that's also helping kind of the ability to do planning through neural nets only, because they're having a more accurate perception of the world too.
Yeah, the more different modalities that they can, modalities, they're you get the most benefit when they're synergistic and they have, but they're very different angles. Like, they both require, like, there's common elements that they both require, but they look at it in a really different way because they cover each other's blind spots. They force the model to learn things in multiple ways, and that fills in more of the gaps in the model's understanding of the root of the phenomena that it needs to deal with to solve the problem you're asking it to solve. Yeah. So like, if they have a pictures in, pictures out component to this, I think that would be really valuable. It's just, I think it's a really difficult technical problem. It really takes a lot of compute. Yeah. It's car Karpathy had this statement about whether your training signal is strong or weak. If your training signal is weak, you need a lot more examples before you get traction. So it's expensive to use a weak training signal. You want to use strong ones when you can. That's one of the reasons why he's a big fan of supervised learning early on, because it has the strongest training signals. That's why he's a big fan of very carefully curated data sets, because it maximizes the strength of the training signal. You could argue that the training signal for pictures in and pictures out is very weak. So, which is one of the reasons it takes a lot. It's a weak training signal that covers like a million different things you're learning simultaneously. So, like the area under the curve of all the stuff that you learn is really useful in that situation. But if of those million things you're only going to use 100 of them, you're spending a lot of time training the model on a lot of stuff that it doesn't actually need to know to solve the problem that you get. So there's this complicated trade-off.
Yeah. I mean, it also is a possibility of like one of the reasons why Tesla is needing so much compute is I was looking back at that one graph that they showed of going to 100 exaflops by end of next year, so October 2024. And it seems like when I looked at the date, it was just released in like, I think early July or something, just a few months ago. And it seems like it was something that came out of this V12 effort, that they realized they needed a certain amount of compute power to reach a certain goal. Do you see like with this V12 effort, they shifted their goals of compute power to be much higher because if there's a specific need? For example, could it be picture in, picture out, or could it be something else that needs a ton of compute that they just don't have right now that would dramatically, improve?
Picture in picture would really require a lot. I think that pictures in to control out, if you need a lot of examples, how sample efficiency is this idea of like the more examples I need to learn something, the less sample efficient my training system is. Mm-hmm. If the sample efficiency of pictures in to controls out is poor, like maybe it's very powerful, but the sample efficiency is poor. And you look at that and you could say, that solves the remaining 5 problems that we need that we didn't know how to do. It's worth spending the money to get this because it solves those, even though the sample efficiency isn't very good. And to overcome the sample efficiency problem, we just need lots of computers. You need a lot of data and you need a lot of computers. Luckily, they already have a lot of cars, so they can get a lot of data. So maybe computers were the one thing they didn't need. I think your observation about the timing is interesting. Like I hadn't noticed that myself. Like now that we're getting these book excerpts, we have to go back and re-examine all the theories that we had previously. But yeah, the timing, it does kind of seem like the timing of that chart coming out was around the time they might have decided to shift, and it might have stimulated them to look. And it might also, it's possible that the infrastructure that you need, like a big part, we knew they had training the neural network and the auto labeler before, which are kind of these 2 different modalities, and each one of them was, I don't know, I think the numbers were like 25% or 40% or something like that. So each of them was a really big problem, and they were going to spend so much time, so much compute time on that having a special architecture optimized for each one of those 2 made sense. So it sounded like Dojo was being optimized for auto labeling. And, other comments that Elon had made about this kind of also suggest that. Like, I think he had commented at one point that, like, the current one is really good at training from video. It's not so good at doing these other generic model things. Version 2 of Dojo will do that kind of stuff. And that might have been happening around the same time, where they were like, we might be wanting less auto labeling going forward as a fraction of all the stuff that we do. And so that would be a shift. If they had stayed on the path that they were on before, where they were gonna keep cranking up the volume of data, training basically the same way. Well, if the auto labeler was half of all the stuff they were doing, well, they need an awful lot of auto labeling, and maybe you want a computer that's specialized to that. One of the things about the photons in to images out, no auto labeling, right? Once again, it's synergistic with these other modes. They're not going to throw auto labeling away. I think it still has a lot of value for what they're doing. But if the amount of training they're doing today is 1% of what they think they need to be doing, right? It could be that they decide to stop the auto labeling portion at 1, 2, 3%, because they need 95% is going to be this pictures into controls out thing. Like that's going to be the recipe that gets them where they're going. Well, if that's where you think you're going in terms of your compute budget, and you were designing a dojo that wasn't as well suited to this, dojo, obviously pictures into controls out, there's pictures there too, right? On that kind of thing. But the pictures processing for that is a bit different. It's more like the neural network training component of the previous process than the auto labeler was. Yeah. So, because the auto labeler, there's a component of it which is just working from the geometrics of the cameras to basically, construct a 3D scene, label a 3D scene, and then you're going to back propagate those labels back to your images and then use those images in your training. So the auto labeler, in a sense, it was kind of more of a geometric, more like a GPU-y kind of, although you wouldn't use GPUs for it. So maybe this is a shift, and maybe one of the reasons why they want to accelerate a dojo too is because now, it looks like the architecture they had wasn't as well suited as they would have liked, and by making a few changes to it, they can get something that will be much faster on the pictures into controls out version. All these things are possible.
Yeah, I mean, so I'm still like a little bit like thinking that the whole pictures in controls out as a final model, I think it makes sense, and that would go in the cars, etc. But as a training model, I feel like you need more of a tighter feedback loop to train the model. Like for example, the whole next token of a transformer or a diffusion, picture diffuses, guess the picture. Like something that gives a quick feedback loop to do a self-supervised model would be something that would make more sense to me in terms of building that foundational model. I mean, could they be doubling down on some of these existing models they have, like whether it's occupancy network or auto labeling or something, or maybe making a new one or something that gives kind of this tight feedback, self-supervised learning approach where they're able to just crank it up and build kind of this, a stronger maybe 3D model first. I don't know.
So self-supervised, if you're talking about supervised, unsupervised, self-supervised is these different kind of training modalities. Supervised training tends to have the strongest signal and tends to have the tightest feedback loop. I mean, you get a tighter feedback loop with a stronger signal. And one of the reasons for that is because typically you just train it on the labels that you need for your application. So you're not wasting a lot of cycles in the neural network having it learn all kinds of stuff that's not relevant to your application. The pictures in, pictures out, that like one of its weaknesses is that it's going to learn all kinds of things about the world that might not help you much in driving, right? One of the beauties of pictures in, controls out is like, well, you know what I want in my model to do? I want it to operate the controls in my car. Like it's the most direct, like in a certain sense, it's the purest signal because you're only ever asking it to learn things it needs to learn to operate the. Now that could include a lot of things. It could be, that, a flock of schoolgirls standing at an intersection is more likely to not be paying attention than somebody in some other situation, right? I mean, that's a pretty subtle signal, not only to see people, to recognize the interactions that they're having and predict whether that means they're paying attention or not, looking at their body language and all that kind of stuff. That's a pretty complicated and subtle signal. But it is a signal that if you have enough examples in the real world, the pictures and controls out, it will learn that thing, right? Whereas, the signs on buildings that you're passing by, right? Like advertisements, like what do the billboards say? I mean, if you're doing pictures in, pictures out, it has to learn to predict what the ads are on the side of the freeway, right? And that might not be relevant to driving. So, pictures in, controls out, it's got a beauty to it. It can be kind of a thin signal, that is like exactly figuring out exactly why the driver did. Because the model has to develop a theory internally for why a driver did every single thing they see drivers do, because it's got to be able to replicate that action. It's got to see the patterns and be able to reproduce those. And so anything that a human driver that might come into their thinking, like in potentially that's something that the model has to learn. It's still a pretty powerful model. It's still really got to learn a lot of stuff. But they are at this point right now where they've got a perception model that basically works, that they can bolt this thing into. Control isn't super hard, so they can put the control on the back end of that. And if the planner, like they are getting traction. We know they are. We've seen the results, right? That what they've told us is they're doing pictures in to controls out, and like I feel like they're getting really good results. So it must work.
That's true.
Right.
I mean, one thing, it's pictures in to controls out. Also, though, they have to do some visualization on the screen, right? So then there's kind of another angle or route that will show visualization as another
So
out,
Andre commented on this. I think the bikini clad Lilu Dallas whatever tweet, if you saw that.
I don't think I saw
Okay,
that.
well, so somebody, I don't know who they are, whose icon is Lilu Dallas on Twitter had posted some comment, and Andre responded to it. And it was along the lines of like talking about essentially where does the vector space still exist, or whatever the deal. I forget exactly what the context of the thing was, but essentially Andre is saying it makes a lot of sense to keep the vector space around. And it was when I was reading that comment, I was like, oh yeah, they still have a vector space because they're using vector space to draw the display. Might not be exactly the same. It could be derived a different way. They could do a completely from scratch network that they are training to do enough of the vector space to draw the display, but they have the display, right? It's a much more kind of straightforward exercise. It's a much more straightforward sort of, sequence of events to believe that the part of the perception network that they have up to the vector space, that they still have that in there, or they have enough of it that they can still extract a useful vector space out of it, and that the planning module is sitting on top of it. The planning module doesn't necessarily have to pull the data from the vector space. It doesn't necessarily have to work on that. You can take a neural network and it can reach right into the brain in the middle of the previous neural network. So the previous neural network, it generates a vector space, but it's using something to make that vector space. And so the planning module can look at that something which is being used to make the vector space and use that for doing its planning and build on top of that. And I think, like in my mind, that's the most plausible explanation for the speed with which they've done this, the results that they're getting today, and the fact that there's still a vector space coming out of the model.
Yeah. I mean, it would make sense to me that it's not starting from scratch, like an empty neural net and doing picture and controls out. It seems like they're building in some their most capable models or something, maybe some adaptations, and it's not digressed or decreased from last year. It's actually just getting better and better. And then they found ways to make this model more and more capable. And then they use this to train it, let's say with the pictures in, controls out, and it just does fantastically much better than,
You could think of it as fine tuning, right?
Yeah.
Like and this was something I was talking about the other day, that you start with the perception network. Their perception network's quite good, right? They really get a lot of stuff out of that. Like if you had an error tolerant planning network sitting on top of it, because the perception network's not perfect, but it's pretty darn good. Yeah. If you had a fault tolerant, planning network, that could kind of read between the gaps on what the perception was good at and not good at, and take that into account when it's making its plans, then the perception network might be really close to done, right? So you might develop your first version of your planning network that bolts on top of that, and you might not start by training it end to end, but at some point you bolt all these things together. You have a complete system that's kind of working. It works pretty good. It's not terrible, and you're fine tuning it with the pictures in, control out. So when you get to the point of the process where you're doing the pictures in to controls out, that's maybe your weakest training signal. It's the one that's going to take the most data, but you've already, gone 90% of the way there. So now you're using it to fine tune, to get those extra nines that you can't get with the other thing. You're not using it to solve the whole problem.
Exactly. I mean, that makes the most sense to me in terms of what's going on with version 12. It also makes sense where it's not going to be that easy to copy per se what Tesla's done, at least immediately, for other companies, because it's not like Elon might have like simplified it a lot by saying, "Oh, it's just photons in, controls out."
Yeah.
But there's
He
a
never
lot
does
of
that.
there's a lot of stuff that is underneath that Tesla's been working on for years that I don't think they just scrapped. I think it's in a way I think a lot of the stuff Tesla's done is almost like sure they could have done it more efficiently and better if they knew that they would have gotten here, but a lot of it I think is important and almost a requirement to get to where they're at. What's your thoughts?
Yeah, and it continues to evolve. Like, once again, you've got your V1 planner, your V0.1 planner in there, and you start training end to end with, the pictures and controls out from a checkpoint of these existing, because, you don't have to go all the way to 0 on the weights. You can start with something that, if you're not changing the architecture very much. And as you train the thing, then the system itself, when you start training it end to end, it can redefine all the interfaces. It becomes one of the things inside a neural network, like everything, all of the, the concepts can flow back and forth and they reconnect to each other in different kinds of ways. And this is the core of how they learn, right? As they keep reshuffling ideas around until they find something that works pretty well. And then they refine them, they'll crystallize into something which is pretty close to what you want. Well, when you put your Lego blocks together initially, you've got these hard boundaries that human beings drew. Like at this point, the bag of bits comes out, and at this point, the vector space comes out, and so on. You've defined those interfaces. Once you no longer need those, right? You train up to a certain point using those, and then you refine past that. The network itself, it can redefine those interfaces. It can shift them around, right? And it can add things to them. It can take things away from them that people thought were important, but that turn out don't matter very much. And it can add things to it that none of the engineers thought was important, but which turns out to actually be important. And that's a very common occurrence in this situation where, you're the guy that designed the system puts it together, and then you run it and it doesn't do quite what you thought, and you look at it closely and you realize you didn't actually understand the problem. Like the training itself showed you something you didn't know. Well, as the engineering team sees the system evolve and examines it and whatnot, they'll be like, if I had an extra layer right here, it would do this. Or if I made this layer wider or deeper, then I'm increasing capacity and I'm enabling it to do something. Like training at that point, when you're training end to end, the system's going to start revealing things to you about the problem that you couldn't see before. And that will help you learn also. So down the road, the system might morph quite a bit. It might get bigger, wider, deeper, shallower, faster, but it gets better, and you learn from the fact that you've crossed this threshold, and now there's this new domain of information that you can get from the model that you couldn't get before.
Yeah. I mean, it seems like, end to end, like this approach is the dawn of.
It's a big win.
The superhuman driving era, where we're going to reach a point at some point where it's like you can't compare human driving with AI driving at all. It's just AI driving is just light years more safer, accurate, better, and it's just and
the GPT, metaphor is actually, I think, pretty applicable here. You interact with GPT-4, and it's just like godlike in so many ways. But on the other hand, it's so stupid in some ways too. At the same time, so you can, because it's not us. It's not trained. It's not doing the same thing. It's getting to a thing that we recognize via a path that we don't we individually don't really grok. So like in some ways they're absurdly superhuman right now, and in other ways like they can't do things like any 3-year-old can do. And I would not be surprised to see similar kinds of things. They need in V12, or FSD, like it needs to be capable of doing the job that it does. But outside that domain, it doesn't necessarily get there the same way that we do. It doesn't need to. We want it to do the job. We want it to do it well.
Yeah. Like when I think about the shift from heuristics to full AI, I think like when you add heuristics, you're trying to kind of tell the system to do what you expect it to do. Like expectation is your goal, and you're trying to get it to meet that expectation. At times it fails. But I think once you go pure neural nets, I think what ChatGPT showed is with enough data, with enough compute and training, it could reach a point where it goes beyond kind of that the expectation kind of boundaries of heuristics, where it surpasses that, where it's like, whoa, how did it get that? It's like beyond what you could have coded, you know? Before that, coding was the goal, or that goal was the code was the goal. But after going purely neural nets and after a certain level of capability, it seems like we've learned that AI can surpass, you know, the boundaries of code into this field of, you know, whether it's called emergent or zero-shot learning, or just this new behavior that's way beyond, you know, what our coding. And that's kind of the era that we're in. It seems like that's what ChatGPT crosses into. It seems like FSD is, you know, on that cusp, you know, getting closer to that point where we're going to be like, you know, I don't know, just surprised at how it drives and how well it drives.
I'm happier with the metaphor that it's got a lot of capability that we don't appreciate because it doesn't express it in ways that make sense to us. Kind of like the difference between GPT-3 and ChatGPT. Like the capabilities are there in GPT-3 to do what ChatGPT does, but ChatGPT refactors those and makes them accessible to people. Now we see the potential. We can use it. We can access it easily. I think, you know, going end to end and training by mimicking what people, you know, how people drive cars has the potential to similarly like be this kind of phase transition for it. And, you know, ultimately the capability does go up, but I think it's going to seem much more friendly, like right away. And that for a lot of people, that's going to be a huge step up. You know, I think people driving V12 are going to be shocked and amazed at how human-like it is, right? Because it's being trained from people, and that's going to totally dominate their impression of the system. You know, maybe there will still be interventions. Maybe there'll be different interventions and that kind of stuff. But I think people's experience of it will just be that it's better, even if the core capability doesn't change. I think the core capability will change. But I think that the way people experience it being so different is actually going to be a huge factor in the thing. And like Elon had made some comment a while back about, you know, FSD having its ChatGPT moment maybe soon or whatever the deal was. And there was that comment that you mentioned from that anecdote that was along those lines. To me, that the ChatGPT moment is that moment where people sort of look at it and they're like, wow, this is kind of amazing. That, you know, not so much that you get the capability, although there's that, right? But that people suddenly realize the capability, suddenly have access to the capability, that they can use it. And that sort of psychological change in the way that V12 will feel over V11, I feel like it could bring about that kind of thing where, you know, you take a completely random person and you put them in your car, and, you know, and they ride as a passenger in FSD for the first time. And we all know like how hit and miss that can be, right? Like some people they don't have positive experiences with the idea that the machine is controlling the car and it's doing these things and they kind of don't make sense. And that could just go away, you know, where people just have everybody experiences that sort of unbridled joy of like, wow, this is amazing. It's doing this by itself.
Yeah. What are some risks of FSD V12? Is it possible that the removal of heuristics going end to end introduces some other potential dangers, you know, maybe some situations where the heuristics were preventing, you know, some things are happening, but then this new V12 version doesn't have those, you know, those boundaries. So yeah, what, I mean, it's hard to predict, you know, obviously without testing out, but what would you imagine to be some of those type of things?
Well, so the intervention that we saw in the demo, you know, the missing the light, that's something that, you know, 11 hasn't been doing. That was common back in V9, maybe V8 kind of time frame, but like in 10, 11 was practically didn't exist, right? So that's a regression, pretty clear. How do you fix it? Well, they said, you know, you get a bunch of examples where how much better does that get you, right? Like what's the current failure rate? If I have 10 times as many examples, what does the failure rate go down to? Like how many examples do I have to get before I get back to where V11 is? That's something that like even the guys they're probably, you know, that all of the work that they did, getting up to say April, if they started in December, January, and they went up to April, that was probably a big part of that was them sort of convincing themselves that they have ways of dealing with this, that the things are tractable, that they're not going to have to resort to plugging heuristic code back in there. I mean, it sounds like right now they basically have virtually none. Like they're trying to just strip the heuristic code out. Mm-hmm. Can you always bolt some heuristic code on? Yeah, you can. It's a lot harder to do if you don't have a heuristic layer in there where the heuristic layer is making decisions. Mm-hmm. Like if you've got a heuristic layer that's written, people wrote it, people understand it, and you have all these simple human understandable switches, mm-hmm. and you want to change the behavior, well, you know which switches to adjust. That's not nearly as easy when it's an end-to-end neural network. You can still put guardrails on it, right? You can, but it becomes really hard to build guardrails that are going to be an improvement to the system, right? Because you're trying to outguess a really, really, really smart system. Like if you could reliably outguess it, well, you wouldn't need it, right? You'd be able to do the job without it. It's so it's hard to do that, and I think to the extent that you can avoid doing it, they want to try really, really hard to not do that. Let's fix it with data. Let's fix it by refining the training. Let's fix it by being more clever about what we're asking it to do. Like you'll see them doing this and trying to understand it. Is it externally, not knowing, what hurdles they've overcome, what things they're struggling with, where the interventions occur? We know so little about the system right now. We can certainly imagine that there could be some big problems, but the system's already working much better than I would have expected you to be able to get to this point, given where they started and how big a change this is. So it may be this is just working great, and they're not too worried about those problems. They feel like they just need to do some refinement. There's certainly potential. I mean, this is an expensive change. Yeah. It may be an expensive change that they had to do eventually, so you could justify it that way. Someday we got to go end to end. Might as well do it today. But, there are a lot of things that they have to do. And there's a lot of work that they've done up to now that they no longer get the benefit of. Like those 300,000 lines, you've been driving it for a while too. Yeah. You saw how much better those 300,000 lines got over the years. And that's value that they don't get anymore. So there are costs, and there are opportunities that they're giving up when they move forward in this direction. And my belief is that they probably see, a benefit that more than compensates them for both the risk and the cost associated with doing this, and that's why they've decided to go down this route. To be fair, we're not going to have a really good understanding because the demo's vague, and demos are demos, and they're only 45 minutes long, and the fact that they made a bet on this, I think, is one of the things that gives me the most confidence in it. Yeah.
Okay, so walk us through how you might imagine Tesla fixing a problem with V12. For example, let's say it's that signal light intervention, that Elon Musk did. I would imagine there's a couple approaches, or many different approaches, but one approach would be just to feed it more of the picture in, control out. Like
that was what
examples,
they said
right?
In the demo.
Okay. Another approach I'm thinking could be if, for example, you have one of these subnets that, like, you somehow test it and then you refine that subnet so that it's more accurately able to maybe discern, I don't know, a certain feature or part of that scenario, which helps it to automatically correct the mistake. Let's say that seems to be another way you could, train a subnet to correct the final control.
If they're just doing pictures in, pictures out, you're much more constrained than if they're building on top of the systems that they have right now. Yeah. I believe they are very likely building on top of the systems, maybe modifying them and making adjustments and that kind of stuff. So in the current system, if the perception system right now, it was told traffic lights are important. You need to tell them apart, and you need to understand which one is relevant to you. There can be multiple traffic lights. And the way that this got done was that there was an output in the previous training thing which says, show me the traffic lights. Where are they? And there's another one which is show me which traffic light is for you. And you train on that. So that concept is baked into the perception system at that point. It has to learn what traffic light is relevant to you because it was telling you for a significant part of the training to do that. So you know that concept is in there. So when you build the planning layer later on top of that, it's drawing from that knowledge and using it, right, to make controlled decisions. Okay, so the planning layer got it wrong in this particular thing. Well, a thing that the engineers can do is they can, if they've got a recording of that, they can play it and they can look at like what it was. I mean, people talk about neural networks being black boxes, and to some extent that's true, but we have all kinds of tools that let us look inside and understand a lot about what is going on, right? You can look at that activation, you can look at what it was considering when it did that, and you can try to understand, is it looking at the stuff which identifies the ego lane? Is there other stuff which is somehow taking priority? Like, is it not looking at the right thing, or is it also looking at some other things and confusing them, that kind of stuff? So that's a thing that you can do to try to debug it. But another really fundamental thing that you can do is you can do more of that initial training that you had. Well, let's train that perception system even harder on this is your light. That is not your light, right? You give it more of those examples, that are similar to where it failed to like fix that. That's the same data engine that they were training before on it. So you can continue doing that, right? And you can, and this is one of the reasons why it's advantageous to maintain that as a parallel training method, and which is you're doing in addition to the pictures in, controls out thing, because it does give you this option of like, instead of where you can kind of reach into the concepts, the perception system, you can change the emphasis it has. Like if they change, there's this thing called a loss function. And the loss function is basically, what do you evaluate in terms of what the network did on a particular example when you provide it with feedback about how it did? Because that feedback on like, you were 99% right on this, or 98 or 97, it takes that feedback number and it decides how it's going to reapportion its weights. So the loss functions on these networks, they're because the output is all of these thousands of different things, you have loss functions that have a weighting for these different factors. So it could be that when you're doing the heuristic, when you have a heuristic planner, you need a certain accuracy on that camera thing that comes out, and you need certain accuracies on other kinds of things, right? But it could be that when you switch over to doing the end-to-end training, that the accuracies that are necessary for the neural network planner, it's a different mix of accuracies that you need. So you can go back into that, you can change the loss function, the weighting in the loss function for the perception system, retrain that with the new perception system, and now you bolt your planner on top of it. So that's another way of addressing an issue like this that doesn't require you to just like, let's brute force it by getting a lot more examples of that. Like, if you can brute force it and you've got the capability to do that, that's great, because it's a really straightforward way of going at the problem. But if you need a more nuanced approach, you need to do some brain surgery. Like that's also, there's more different ways you can do the brain surgery if you have these alternate training systems that you're also using.
Yeah, that makes sense. I mean, so going forward, what do you think is kind of the flywheel? Like what's the process of, V12 improving over time? Like, what is it similar to the previous kind of data engine where you have an intervention, a failure, then you look at that and you send out requests, for that scenario, you bring it back, you feed it back into the system, either through the, picture and controls out, or through more of a different subsystem or something, and you try to fix it. Is it similar to that, or is there some adaptation or different approach you think that they'll do?
Well, we know Ashok mentioned in the drive that they were going to push shadow mode out, right? So the shadow mode in this case is not going to be, it's probably not shadow mode FSD. It's probably, they're putting a shadow mode V12 in all the non-FSD cars, because you're watching drivers do that kind of stuff. Because the shadow, to do the pictures and controls out thing, you want lots of examples of humans driving the car, right? So you really want to put it on the cars where people are rarely or maybe never using FSD. And then in that situation, in shadow mode, right, when the V12 system, it's driving along, running on the cars, basically saying, if it was me driving, I'd do this. If it was me doing, I'd drive that. And then so you have this little module that basically looks at what the car would do in this situation and what the human did do in that situation. And it tags interesting examples, especially it's going to very likely be similar to what we saw with the way triggers were pushed out to the fleet, where the development team would decide there's this category of stuff that we're having problems with, and more examples of this kind would help us. So you make a fingerprint of that example, you push the fingerprint out, and then as the cars drive, they're looking at the situation they're in, comparing it to the fingerprint, and when they get a match, they capture it and they send it back. So similarly, the shadow mode thing, it would have a fingerprint. Like here are situations where if you deviate from what the driver does, please capture that and send it back to us. It'll be a fingerprint for the situation. So similarly, shadow mode will be running, but in this case, the shadow mode is like a full V12 stack running in the car, not controlling the car, just basically saying what it would be doing, and then it compares that to what the human driver is doing. And for a class of drivers and a class of situations, it does a capture and sends that back, and then then the labelers can look at that and see, does it address the question? And there are various layers of curation you can do, where the team can decide, yes, if we include this example, it actually helps make the problem. Or if we include this set of examples, it makes a problem. And so they add those to the permanent training set and move on to another problem.
So we've got this fingerprint that, let's say, Tesla sends out of different scenarios it wants to capture. Could they also be capturing, let's say, non-FSD cars running shadow mode at V12? V12 shadow mode is predicting what it's going to do, and then it's similar, and then one instant it's very different. The human does something very different than what it would do. Could that be like a trigger to send the video clip as well?
The triggers are almost always going to be the human did something that shadow mode did, because they're specifically training it to mimic people. So so this is kind of interesting. When you do a lot of kinds of discrimination that you do with neural networks, you give it good examples and bad examples. You show it a picture and you say, is there a tree in this picture? And the answer could be yes or no. And sometimes it's right in one direction, sometimes it's right in the other direction. So you have positive and negative examples, and you train on both of those. In the kind of training where you're training it to mimic a human, you only have positive examples. And that's one of the things that makes the signal weaker. You can't give it negative examples. There's not a really straightforward way to say never do this in this situation. The examples are almost all of the form, this is the thing you do in this situation, this is the thing that you do in this situation, right? So the training examples they're looking for they're going to be almost exclusively, this is for the pictures and controls out, they're going to be almost exclusively of the form, the system said press the gas and the human hit the brake, or the system said speed up and the human slowed down, or whatever. They look for those deviations, but there are going to be so many of those deviations that, especially they're going to need to down select those. And so the fingerprint will be like the light thing. It may be that there's a right following distance. And so you're like driving down the street and you speed up or slow down to match the car ahead of you. But some humans drive closer, some humans drive farther. There's going to be variation in that kind of stuff. And it may be that, the guys that are evaluating the V12 performance are like, its following distance is great. We don't need to mess with that. So you never capture the following distance things because you've basically got that problem solved. On the other hand, if you have which light is the ego light, which is the one that I need to look at to decide whether I go or stop at this light, like if that's something it's not, then you specifically send a trigger. If you're stopped at a stoplight and the light changes and you think go and the human says stop, send me that one. So that's a fingerprint, right? And you probably want to go farther than that. You want to say, intersections with certain characteristics, it's not mostly failing the lights. There are certain lights it fails on. So they'll go back and they'll look at the lights where it fails, they'll make some guesses about what the common denominator is. Or you can actually do a thing where it worked on these 100 lights, it failed on these 100 lights. And you can do a fingerprint thing where you take fingerprints of all the ones that worked, all the ones that are different. You take the difference between those two, and then you generate a fingerprint, which is like, this is the difference that the system sees between where it works and where it doesn't work. When you see those, send me those, right? So you don't even necessarily have to figure out what's wrong with it. If you've got examples that work, examples that don't work, you can do this kind of numerical processing thing where you send a fingerprint out, which is the difference between those two, and you ask the system to specifically look for that fingerprint.
Interesting. Do you think let's say FSD V12 shadow mode, do you think it's going to rate the drivers where, for example, some drivers are just not good drivers? They're just driving too fast, not enough space, all this stuff. You don't want, per se, maybe, their driving examples that much, but there's maybe these 5-star drivers that are just model drivers, and you want to give preference to those drivers and their video data. Do you think there's going to be anything like that going on?
Yeah, I mean, they already alluded to, you only want the good driver data. Where do you draw the line? How do you decide who's good and bad? Maybe some people are good in some situations and not in others. It can be kind of complicated. There's also this question of do they have all the data they need? If you're getting way more data than you need, you can afford to throw away most of it. And you can have these very simple brute force filters that still get you what you need. There may be situations where you have to get, like the whole thing with the, human beings don't stop at stop signs, but we need to train to stop at stop signs, right? So do you find the people who always stop at the stop signs, or do you just look for examples where somebody stopped at a stop sign? If you have lots of examples of people stopping at stop signs, you can throw away a lot of them. But if they're precious because you have so few, you might have to put more work into filtering it. And that might be where the labelers come in. Labelers have to, on a case-by-case basis, was this a good stop? Did we add this to the database? Right?
Yeah. I was thinking ideally you don't want human reviewers or labelers to be in the process, but it seems like, especially early on, you want the quality of data to be pretty high. You don't want bad data to go in too much. So I don't know. Do you think they're reviewing a lot of these, things that, for example, I don't know, if there's a discrepancy, let's say, between how a V12 would handle and a human driver, do you think there's actually human reviewers right now?
For some things.
For something.
For sure. There will be. And I mean, you could replace almost all of them with enough compute, because one of the things that you can do is say that you've got a system and you want to ask the question, well, if I add these training examples to the training set, does it solve this problem? Well, what you do is you tentatively add them to the training set, train it, and then you regression test it to see, well, does it break anything else? If it not, does it solve my problem? That's just a really compute intense way of resolving the problem. You can do that. Right. And so if compute is cheap and people are expensive, maybe you do more of that kind of stuff. There's probably a blend. There's going to be some things where, to solve the problem would take a lot of compute and a relatively small amount of labeler time. And so you definitely do that with labelers. And you're going to have the opposite example too. There can be places where it's just going to take a lot of labeler time, so we'll spend the compute instead. And we do that. I think they probably have internal processes for doing both of those things. But they basically said, labelers do this, labelers do that. They still have labelers. The labelers, the job is more like curation. So labelers, in a case where you actually have a label, stop sign, not stop sign, this speed says 55, 45, 35, whatever it is, they're actually tagging that stuff. If the only decision a labeler gets made is include this or not include it in the training data, it's more like curation. Right, we're not going to put that in the set. We are going to put this in the set. In a sense, they're pretty similar jobs, but you need similar people with similar skills to be able to do both of those jobs, and so it's probably the same people.
Yeah, there are some people saying that Tesla's been hiring FSD drivers, and one person is saying that in Australia they've been hiring FSD driver in every state. Why do you think Tesla's doing that? Is it just early on with V12 to get the good data, basically?
I mean, these rumors have been around for a long time. I mean, they're not rumors. I mean, they're hiring. They're hiring notices on the website. We know that they're doing it. We don't know how many there are, where they're located, that kind of stuff. Not in detail, but we know they've been hiring people. And I think the expectation had been that what up until now, that people were getting paid to drive FSD 11 or whatever around foreign countries to see how well it worked, places where it isn't deployed right now. And in hindsight, we can say, well, probably one of the things these people are doing, maybe the only thing that they're doing, is driving V12 and gathering good driver data in a variety of, because one of the things, especially early on, that you really benefit from is having your training data have the highest possible diversity in its settings. The road signs, the weather conditions, the lighting conditions, the traffic conditions, and so one way to get a ton of diversity is like, let's hire 1,000 people as widely distributed around the planet as we can. Let's screen them to see if they're good drivers. Let's give them training. Let's give them a guidebook and get them to do that kind of stuff. And let's give them directions. Go out and do this and do that. And we're going to, use you guys to gather this initial training data that we want to do this stuff. Like, it seems really likely to me that that's a component of what's going on.
Interesting. All right. So sadly, we're running out of our 2-hour time allotment. I feel like we're just getting started. I only actually covered like a tiny portion of the questions or topics I wanted to cover. I have like 30 or 40 questions from Twitter. I feel like some of these, like, we can go on for days. It's such a fascinating topic. I don't think it gets enough thought and coverage. Everything's focused on other parts of AI right now. It doesn't seem like FSD and what's going on underneath the hood and what Tesla's doing gets enough recognition, but
it's starting to change.
Yeah, I think
hopefully it'll change more.
Yeah. My hunch is maybe they'll not do an AI day this fall. I don't know. It seems like there'll be.
It's been a year.
Yeah, it just seems like it'll be such a busy time right now getting V12 up and going that maybe you push it to spring or something. I don't know, after the first release.
I think it's probably. They said explicitly it was a recruiting event, both of the first 2 years that they did it. It was really clearly, I got to go last year, and it was really clearly a recruiting event. That was 99.9% of what was going on there. So, it could be that they're not feeling as much, pressure on the recruiting end of things as they had before, maybe. But yeah, I hope they do another one. I would like to learn more details. Maybe they're at a point where they're feeling like if we had, in another 3 months, we'll be able to put on a more impressive show, and so it would be more effective, or 6 months from now or something. Yeah. Or maybe they are just really hot and heavy on work, and they don't want to, distract the team with it.
Yeah, it's interesting. With what you know now of V12, does your kind of Robotaxi timeline expectations, like, how does that get impacted at all?
Like, in short term, sadly, I feel like it kind of pushes it out a little, but because now I know they made this big change, and it takes a while to digest it and understand it, and and become as confident with it as you were maybe on the previous approach that you had. Like, it's a change. The flip side is it seems like they're much closer to the optimum, final state of the product than they were before. So what are they waiting for right now? Like, is V12 as good as V11? And they're just, are they still developing? Like, do they have a bunch of problems? Are they still trying? Is that the issue, that they have things they're trying to take out? I don't know. Is it that they just need more confidence and they want more time on the road with more people before they turn it loose on drivers? I don't know that either. I would have thought that maybe the OG testers, would have pushed it out to a smoke. Maybe there's a different group of OG testers that are under NDA that are driving it, or maybe they've decided that they're only going to use employees. Maybe they're waiting for regulatory. Elon had said, the next FSD it's not going to be beta. V12 is not going to be a beta version. And it may be that if it's not a beta version, they have a higher regulatory hurdle to clear before they feel like they can push it. Maybe they're waiting on that, and it's some external party that they're trying to convince that it's good. Like, at this point, we don't know what it is. Like, the most optimistic thing is, like, they feel like it's ready to go, and they're waiting on the paperwork. The least optimistic is, we think in 6 months it'll get to where V11 is on interventions. Like, that might still be good if your learning curve is really fast. That could still be a really significant win. I think previously I had said I thought there's a 25% chance that it could technically be capable of unsupervised driving better, safer than a human this year. 50% by the end of 2024, and like 25% farther out than that. Right now, that still feels like the right ballpark.
Interesting. Yeah, for me, I I've been slightly more 2025-ish as the unsupervised,
Mm-hmm.
but I thought that the initial rollout would be kind of slow because of, I don't know, just it's a tough problem. But this changes my view in the sense that I think the rollout could be actually faster because I think the capabilities are improving faster. I think the next 3 to 6 months might not be like just these new problems that are introduced might distract people, and it's we're not going to see, I think, this superhuman model within the next 3 or 6 months because of the things they need to work out. But fast forward a year to fast forward 12 to 18 months, and I'm much more optimistic at how much the
I'd say
capability
that
changes.
generally characterizes my response too. But that said, we don't know where they're at in terms of like what the actual intervention rate or how serious the interventions are.
I would
that's
love
a big constraint.
I would love to see that one interventions per mile or figure.
What they have on the display.
Exactly.
In the room. Would be...
I wouldn't mind one in my house. Just like every day, but fine.
Although it might be like watching the stock price.
That's
right?
True. Goes up one day.
Goes down. It's really noisy. You spend a lot of time being depressed for no reason.
Exactly. Do your expectations of the humanoid robot timeline change at all because of FSD V12?
Wow, that's a good question. I don't know. The controls. I think the single most important kind of step forward the benefit that they got out of this doesn't apply nearly as well to the robot as it does to the car, because if you instrument a human and have a human go around and then you train the neural network to like move the body the way the human does, that's a thing that you could do. But one of the things we know that training robots in simulated environments with reinforcement learning, that works really well. And that's something that doesn't work as nearly as well in cars. It's because of the safety, conservatism, necessity for speed and that kind of stuff. So off the top of my head, thinking about this for 3 minutes, I don't think it makes nearly as big a difference to Optimus as it does to the car.
Interesting. Cool. All right, James, nice chatting with you in person again.
Likewise. It was great.
Yeah. Always fun to catch up. And it's interesting. It's going to be interesting next year or two of following Tesla's FSD improvements. And
the next year is going to be really interesting for sure.
Yeah. I just don't think that people are mentally prepared for how much robotaxi autonomous driving is going to change things and how quickly it could change things too. I just feel like, there obviously will be a supply issue of the number of cars that Tesla can produce, but it just seems like it's going to be a tidal shift of change. And if you add autonomous driving with humanoid robots, go out 10 years, it just seems like it's a different world.
10 years. Yeah. Things really change a lot. Yeah. We live in interesting times.
Definitely. All right, James, thanks again. I'll talk to you later.